Okay, welcome to the fifth week of our machine learning course. Today we will be covering support vector machines. That's an important topic for machine learning. There will be some mathematics for today's lecture, but I hope that's not gonna be too overwhelming. That's the outline of this week. We will be starting as usual with the summary of the last week. Then we will work on a concept called linear separability. And then we will be starting the theoretical part of the support vector machines. After that, we will be doing a lot of examples in order to understand support vector machines, how we can use them and how we can use them for a problem called multi-class classification. As you remember from the last week's lecture, we started with binary classification, which means we actually had two classes, class 0 and class 1. And today we will be starting the concept of multi-class classification. Okay, summary of the previous week. Last week we basically worked on binary classification. We made a definition of classification, what classification is, and we started with a simple classification called logistic regression, which is a binary classifier. We saw that this equation can basically be used in order to classify our classes. And then we worked on an example called the MNIST handwritten digit database in order to classify the 0 and non-zero digits. Then we have seen some concepts called precision recall. We saw something called confusion metrics as here. And then we saw some accuracy assessment and performance evaluation metrics, accuracy, precision recall, and F1 score. Then we have seen how we can use this precision recall curves. And then we have seen another concept called ROC curve. So coming back to the logistic regression, we saw that that's a binary classifier. It decides whether an observation is from class 0 or class 1. That's based on the logistic function, also known as the sigmoid function, which is this equation. And that's called sigmoid function because of its shape, as you see here. That looks like an S shape, that's why it's called a sigmoid function. And we have seen for n independent variables, the probability of being class 0 is calculated with this equation. And given each training instance, we calculate a prediction using the current values of the coefficients. Then we calculate new coefficient values based on the error in the prediction. And the coefficients are updated based on the following equation. Then we worked on this MNIST dataset. Some examples you see here. So the MNIST database is a dataset of handwritten digits. It contains 60,000 training images and 10,000 test images. We will be doing another example today. Last week, we actually tried to make a classification on whether a digit is a 0 or a non-zero. This week we will be doing a classification, a multi-class classification, and we will try to classify whether a digit is 0, 1, or whichever digit is. So it's not going to be a binary classification, but a normal multi-class classification. We have seen the usage of MNIST database. I provided you the code and the sample data so that you can try it yourself as well. We have seen that that's a 28 by 28 pixel digital image. This data, these digits are pretty small images. And we have seen that the X train contains these digits and the Y train contains the labels. So we were able to make the classification. Then we have seen the concept of performance evaluation for classification. We saw something called confusion metrics, as we see in the left side. So we have our actual predictions, we have our actual data, and we have our predictions, okay, in the confusion metrics. See, on the left side, we have the actual data, we have on the top our predictions. And we have seen concepts called true negative, false positive, true positive, and false positive, false negative. So these are pretty important concepts for machine learning. if our actual data is a negative and we made a prediction which is negative, that means that's a true negative. That means we classified these correctly. Okay. Similarly, if our actual data is positive and we could be able to classify this as a positive, then that's a true positive. And if our actual data is negative, but we classified this, we predicted this as a positive. So this is negative, actual data is negative. That's how you read the confusion matrix. The actual data is negative, but our prediction or the classification is positive. That means that's a false positive. And if our actual data is a positive, but predicted this as a negative, that means we couldn't find it, for example. That's a false negative. So that's how we read the confusion matrix. And based on these values on the confusion matrix, we saw 4 performance evaluation metrics. The first one is accuracy, which is basically number of correctly classified samples over number of all samples. But we have seen that accuracy is not really a very good metric for performance evaluation, because coming back to our digit classification example, we have 90% of our data as non-zero and 10% of our data as 0 digit in our MNIST database. And if we wrote a classifier which is basically saying everything is a non-zero, its accuracy is basically 90%, which sounds pretty good, but that's crap, because it's just saying everything is non-zero. That means actually accuracy by itself is not an enough metric. It's not enough for performance evaluation. So we have seen 2 concepts, precision and recall. And basically the formula of the precision is true positives over true positives plus false positives. And recall is true positives over true positives plus false negatives. What recall means basically is how many of the items we could be able to find, and precision is how precise, how accurate we could be able to find what we have found. Okay, so the precision and recall, these 2 terms are used in combination. You don't use just precision or just recall. If you want to use precision concept, you need to use recall concept as well. And similarly, if you want to use recall, then you need to use precision as well. And then we have seen another metric called F1 score, which is basically the harmonic mean of precision and recall. That's the equation of F1 score. If you would like to use just one number as your performance evaluation metric, then F1 score is a good metric that encourages both high precision and high recall, because as you see, both in the numerator and denominator, the precision and recall has the same value. But if your precision is low, for example, then even if your recall is high, then you will not be able to get a high F1 score. As F1 score is basically the combination of precision and recall. So coming back to how we were able to read this confusion matrix, that's basically precision is the right side of the matrix, because it's basically dealing with positive predictions, and basically the recall is basically dealing with the bottom side of the matrix. That's how you could remember. But please try to understand the precision and recall concept. They're pretty important for machine learning. So what precision is, just to summarize, let's say you're trying to classify dogs and cats, okay? If you call a dog, then that's a true positive, right? But if you call a cat a dog, if you couldn't classify this cat correctly, if you classified this as a dog, then that's a false positive, okay? And that's what precision deals with. You deal with true positives and false positive, whether you could be able to find the true samples and whether you make an error while you are trying to find the true samples. That's what precision deals with. And what recall deals with is basically, again, the true positives and false negatives, which means there was a dog, but you couldn't classify this as a dog. Okay, that's a false negative, that's an error. So this is an error as well. The false positive is an error, false negative is an error. If you could be able to classify something as true positive, then you are good. And recall deals with true positives and the false negatives. And we have seen this precision and recall curves, and we have seen this ROC curve. Basically, you can use precision recall curve in order to determine a good threshold. You can just observe how much your recall is decreasing as your precision increasing. Then you can determine basically a threshold. And you can use the ROC curve, area under the curve, in order to identify whether your classifier is a good classifier or a bad classifier. I'm coming back to the quiz of the last week. Logistic regression is used for classification. That's what it's used for. MNIST is a database of handwritten digits. TP stands for true positive. The formula for precision is true positive divided into positive plus false positive. You need to know this by heart, the precision and recall formulas. SGD stands for stochastic gradient descent. Remember, there was an agent trying to go downside of a hill. F1 score favors both high precision and high recall. And polynomial regression is still type of linear regression. That's true. That's from the previous week. If we aim for very high precision, it is likely that the recall value may drop. That's true. That's what we have seen with the precision recall curve. If the predicted class is positive, but the actual class is negative, the prediction is called false positive. And X and Y axis of ROC curve shows true positive rate versus false positive rate. It's not precision recall curve, it's ROC curve. Most of you made this wrong. You need to be careful about the ROC curve. That's true positive rate versus false positive rate. Okay. Let's start the content of this week. We will be starting with the linear separability. So what is actually linear separability? Two sets are linearly separable if there exists at least one line in the plane with all of the blue points on one side of the line and all the red points on the other side of the line. Okay, so we have these blue points here, we have these red points here, and this set, this whole set, is called linearly separable if there is even if a single line that can separate these two sets. Okay, that's called linear separability. Three non-collinear points in two classes, if you have positive and negative two classes, binary classes, they are always linearly separable in two dimensions. Okay, if you check these examples, for example, we have two minuses and one plus, that's linearly separable because I have a lot of lines that can separate these two classes, right? And that's similar for this case as well. If they were collinear, that means they were on the same line. If that minus was here, for example, that was still linearly separable. But if this minus was here, right, they are collinear and they were not going to be linearly separable. And if you have just one class, that's obviously linearly separable because this is the class itself and the rest of the space. But however, not all sets of 4 points are linearly separable in two dimensions, as you see in this example. So we don't have any line that can split this space so that the pluses, the blue pluses and red minuses will be on other sides of the line. Okay, that means this is not linearly separable. These guys are linearly separable. Okay, so more examples about linear separability. These two sets are pretty linearly separable as well as these two sets because there is at least this line that can separate these two sets. But as you see, these guys are not linearly separable because even if I have a line over here, that's not gonna split these two sets into two because this triangle will remain here. Okay, so this is not a linearly separable set. And this is definitely not a linearly separable set because you could only split these two sets with a circle, right? If we had a circle that's surrounding these blue dots, that would split this two sets into two. But if we want to use just a line, there is no line that can split these two sets into two. Okay, I guess that's pretty clear. Okay, we can split these sets, but there are some lines that might be better than the other lines. For example, this one looks a better splitting than this one, right? Because this somehow looks fishy. It's close to this point, it's close to this point, and this looks like much better, right? So this concept we will be using with our support vector machine. We would like to find so-called the ideal line that splits these two classes so that the distance between these points, the closest points to the line, is highest. Okay, that's what actually the support vector machine does. For example, in this case, this guy is pretty wide, but this guy is pretty narrow. Okay, and we call these dashed lines, this dashed line and this dashed line, the gutters of the classifier. So this is the separating line, also called the median line. Okay, please remember this terms. This is the median line, and these are the gutters. And for linear separability, what we would like to do is we would like to get this width as high as possible. Okay, so we would like to have the distance between two gutters as big as possible. So this is therefore a better separation than this one because this distance between two gutters is not big enough. Okay, so what if we would like to create our support vector machine as simple as possible? So we have an iterative way of doing that. Then we will see how mathematically we can drive support vector machines, and then we will be working on the more advanced support vector machine. But to start with, in order to understand how support vector machines work, let's work on a simple example. So we would like to split this data into two. We actually start with a random line and a random margin around it. Okay. So basically, these three equations represent the same line. It's just you multiply both sides with 2. Since this is 0, that remains as 0, and these guys become twice as big than this one. And if you multiply this guy with 5, for example, you get 0 this side because that's 0 multiplied by 5, and you get this line. So basically, these three equations represent the same line. Okay. But if we modify this equation, we get lines parallel to each other. What we basically did is actually the left side of the equation remains same. We put 1 to the right side of the equation. That's the original equation. If you put a -1 on the right side of the equation, this line goes below. And if you put a 1 on the right side of the equation, this line goes up. Okay? So that's we somehow expanded the line. And if you multiply with a large number, the lines get closer. Okay, as you see in this example, if you multiply the equation with 10, for example, the lines get closer. And if you use a small number, the lines split apart. So if you want to expand these gutters, for example, let's say this is the median line and these are the gutters. If you multiply with a small number, then the gutter expands. And if we multiply with a large number, the gutters shrink. So this is basically how the support vector machine algorithm works. That's a lot more complicated because we will see something called the kernel trick. If we use support vector machines in a linear case, then that's how it works basically. But if we want to use support vector machines in a more advanced scenario, then it's much more complicated. But just now, let's assume that we would like to just use support vector machines to split this two sets in a linear way. Okay, so we start with a random line with an equation ax plus by plus c is equal to 0. Okay, and we draw lines with equations 1 and minus 1. These are basically the gutters. Then we pick a large number, such as 1000. That's going to be the number of repetitions, or what we have seen in the last lecture. These repetitions are called epochs. And we pick a learning rate. Remember from the last lecture what learning rate was? It was basically the width of the step our agent was able to take in one step. Okay, how far it can go, how far our agent can go with the stochastic gradient descent with one step was our learning rate. And then we pick an expanding rate. So we were going to expand our gutters either inside or outside, but we will be expanding our gutters, right? And this is basically the algorithm, and we will be repeating this 1000 times. Okay, we pick a random point, PQ. That might be any one of these points. Okay, and we will be doing this whole procedure 1000 times. And if the point is correctly classified, that means that this equation is correctly satisfied, we don't do anything. Okay, and if the point is blue, if the point is one of these guys, but the equation says a times p plus b times q plus c is greater than 0, which means we classified a blue point as a red point, since this is greater than 0. Then we subtract 0.01, which is our learning rate, remember, with p, and we subtract this from a, and we subtract learning rate times q from b, and we subtract learning rate from c. If the point is red, if we selected pq as one of these guys, but the equation says it's smaller than 0, okay, then we do the opposite of this equation. We subtracted this guy from a, now we add this guy to a, okay, and once we do this 1000 times, then we make an expansion, then we got our support vector, that this is called our support vector. That's basically the very basic algorithm for support vector machines. Before we go into the details, mathematical details of support vector machines, let me share you our first Python example for this week. What we will basically do is, actually we will create a data set with two classes. So these guys are from class 0 and these guys are from class 1. And then we will try to find the line that splits these two data linearly. Okay, so that's how we loaded our data sets into our data frame. We basically give a name to our columns, that's width, height, and class. And once we check the head of our data frame, there you see our first row, here our first row as well. So if we actually plot this, we obtain something like this. Okay, so our this is linearly separable. This is definitely linearly separable. And basically, if we put a line here like this, that's gonna split these two sets. But from my point of view, this is a much better line. And let's see what our custom support vector machine algorithm does. This is basically how we coded what I have shown you with the slides. What we do basically is we select an epoch rate that was 1000. We have an expansion rate that was 0.99, and our learning rate was 0.01, as you see in this example. So this is basically the Python implementation of this algorithm. So it's Python implementation of this algorithm. So if we go through that, we select a random point, and if the random point is a blue, like this one, but it's classified as a red, then we subtract this equation from A. And if it is vice versa, if we select something red, but if it's classified as blue, then we add this equation to A, B, C, and A, B, and C. And then at the end, we multiply A, B, and C with expansion rate, the expanding rate. And that's basically what we get. Let's try. So that's pretty fast. And one thing you should remember with support vector machines, if you have too many variables, then support vector machines really work slowly. But since we have just two independent variables and we have very few samples, the support vector machine work pretty quickly, right? And once we plot our newly generated support vector machine, that's basically the line equation. This is something, that's what we got, basically. That's not the perfect line that would separate the two data sets, but this is a very, very basic implementation of support vector machines. But please remember, support vector machines work differently. They work, there is quite some mathematics behind support vector machines, which we will be dealing in the second part of the lecture. But if you want to implement something that can linearly separate these two data sets, then this is the algorithm you should go for. That's very easy to implement. That works pretty fast, and that can do the job for a binary classification. Okay. Now let's see what this support vector machines does. We will have a brief introduction and then we will have a break. So SVM maps training samples to points in space so as to maximize the width of the gap between these two categories. Okay. So these are all lines. This is not separating these two data sets in a good way. So this is not the line we are searching for. Okay. H2 is basically separating these two data sets linearly. But as you see, that's not really ideal. I mean, if there is a point right here, I would expect this point to be this class, the black class, because that's closer. I mean, but if you use this line to split these two data sets into two, then if we choose an unknown point here, then the point will be from this class, which is pretty absurd, right? But if we use this H3 as the splitting line, this is basically guaranteeing you the maximal margin between two data sets. So this is a much better line than H2. H2 is a much better line than H2. So our aim in support vector machines is to find H3. And there will be a mathematical derivation for the support vector machines. Before going into the details, I would like to make a quick reminder about the dot products, how we could use them geometrically. You should remember this stuff from calculus and linear algebra, but even if you forgot, the dot product of two vectors, basically A and B, is given by this equation. That's basically you multiply A1 with B1 plus A2 multiplied by B2 and AN multiplied by BN. Okay, that's a pretty easy definition of dot product. And if these vectors are identified as row vectors, this is a row vector. If this was in this direction, it was going to be a column vector. This is a row vector. If these two vectors are row matrices, then the dot product of these two matrices can be written as the same equation can be written as this. Okay, A times transpose of B, right? And there is actually a geometric definition of dot products. That's why I'm showing you all these equations basically. If we have two vectors called A and B, and if we would like to find the length of the projection of A onto the vector B, that's basically the A dot product B, given that B is a unit vector. Okay, so if we would like to find the length of A, that's basically the length of A on top of B. That's basically the length of A times cosine theta, right? Where theta is the angle between vector A and B. And this same equation can be written as this: A dot product B. B is the unit vector of vector B. A is the vector A. So we will be dealing a lot with this distance, the projection of A, the vector A, projection of vector A onto the vector B. So we will be using this guy a lot. So let's make the problem definition. We would like to find the line that separates two classes. We have minuses and pluses, okay? And the mathematical derivation, we will be using this very simple example for the mathematical derivation. So we have two classes, pluses and minuses, okay? And this is somehow doesn't look okay, right? May not classify points close to class borders, because as we discussed in the previous examples, if we select something here, for example, then we would expect this point to be inside this class. But since this line is splitting in a way that this part of the line is pluses and this part of the line is minuses, if we select something here, that's gonna be minus, but that's obviously a plus. And this is too limiting. This is another line that could split this data linearly, but that's too limiting for minus class. And the boundary plus is too wide. I mean, if you select something from here, that should be a negative, but that's basically because this line is here, that's going to basically classified as a positive. And this is too limiting for the plus class here, this line. So ideally we should have something like this. Okay, we would expect a median line that's splitting these two classes, something like this. So let's make some definitions. So these are our classes, the positive class, these are class instances, these two minus instances and two plus instances. This is the median line. This is the line that's splitting the class, and this is the gutters. Okay, these are the boundaries, and what we would like to maximize basically is this gutter. So we would like to find the line that has maximum width between two gutters. Okay, so that's the problem, mathematical problem or the geometrical problem we would like to solve. So to start with, let W be a vector that's perpendicular to the median line. Okay, if this was long enough, this vector was going to be perpendicular to this line. Okay, this is any vector perpendicular to the median line. Okay, we don't know its length yet, so it's important to know its length. That's something we will try to find out, but for now we don't know its length. We just know this is perpendicular to the median line. Okay, and let U be a sample. That's one of the samples from any class that we would like to classify, and we would like to know whether it is on the right side of the median line or on the left side of the median line. Okay, so we are slowly getting there. So to find the length of U in the direction of W, so remember our W, that was a vector that was perpendicular to the median line. Okay, and we would like to find the projection of U on top of W, because we would like to find the length of u in the direction of w. That means we can basically use the dot product and we can write an expression something like this. Okay, w dot product u is greater than or equal to c. C is a constant. Okay, any constant. And for now, let's write c is equal to minus b. So this equation becomes this: w dot product u, these two vectors, plus b, that was minus b over here, is greater than or equal to 0. Okay, this is our first equation. So this is our decision rule equation. Okay. So for now, we would like to put some constraints. We will be solving a constraint maximization problem today. So we would like to put some constraints. Okay. So remember our equation. So if we convert this equation into this, w dot product x plus b is greater than 1. That's because x plus is a positive sample. Okay. And our second equation is when we have a negative sample, w dot x minus plus b smaller than minus 1. Right. So this is the equation we used to write these two equations. Okay. So for mathematical convenience, we would like to introduce another variable called yi. Okay, and yi is plus 1 for positive samples. For these guys, these are positive samples and these are negative samples. And yi is minus 1 for negative samples. Okay. So we have equation 1 and equation 2. If you multiply both sides of equation 1 and equation 2 with yi, what we get is basically, let's work, for example, on this one, for the equation 1. Okay, we multiply both sides with yi. And since for positive samples, and these are the positive samples, yi is 1, we can rewrite this equation as this one. Okay, because yi is equal to 1. So this is our first equation that we came from equation 1. And this is the equation 2 here. Okay. And we multiply both sides with yi. And since x minus is a negative sample and yi is minus 1, we can rewrite this equation. Remember, if this is our equation, for example, minus 2 smaller than minus 1, we can rewrite this as 2 is bigger than 1 if you multiply both sides with minus 1. So we can rewrite this equation like this. Okay. And as you see, these are basically the same equations. So we can, with our mathematically convenient introduce variable yi, we can rewrite both equation 1 and equation 2 as this one. Okay, this is this equation and this equation. yi times w dot xi plus b minus 1 is greater than or equal to 0. So now we have this equation. Okay, and if our points are on the gutter like this one, this equation becomes this one. So that's not greater than or equal to 0, because if something is greater than or equal to 0, that's on the positive side, otherwise it's on the negative side. If the randomly selected point is on the gutter, that means we have this equation. Okay, from this equation we derive this. So this is our constraint. Okay, for the samples that are on the gutter. Now we want to find the width between two gutters. So these are two gutters. In order to find, we need two samples. One negative sample that is on the gutter, okay, and one positive sample that's on the gutter. Let's create two vectors for that. Okay, like this one. This is the negative vector, x minus vector. This is the x plus vector. Okay, and the width of the gutter is basically x plus minus x minus this vector projected onto W. But remember, if we want to project something on another, if we want to project a vector on another vector, we need to have a unit vector. So this is the unit vector of W, okay? And this guy over here is this vector, the one that's in red, okay? And the width of this vector is basically the projection of this vector onto W. Therefore, this is our width. Okay, so now we have this equation, okay, for the samples that are on the cutter, and yi is plus for positive samples, which means we have this guy. W dot product xi is equal to 1 minus b, okay, and for yi is since yi is minus 1 for negative samples, we have this guy over here as this equation, okay, which means this expression over here, the width we calculated in the previous slide, becomes this one. So the width of gutter is basically this one, and what we would like to do is maximize this thing, okay. Remember the definition of support vector meshes, we would like to have the maximal width as possible. So we need to somehow maximize this equation. So since this is a 2 here, we can rewrite this equation like this one. Maximizing this one and this one is exactly the same thing. Which means actually if we want to maximize this thing, we need to minimize basically this, okay. And for minimization problems, remember, in order to neglect the effects of negative numbers, we would like to have the square. So we can basically, for the mathematical convenience, rewrite this as minimizing this function. So instead of minimizing this, we would like to minimize this one. Okay, so we have these two equations, and we have the third equation that we would like to minimize. Okay, so now we have my handwriting, which means things are going to get fishy. So in order to solve minimization problems with constraints, basically this is our constraint and this is the thing we would like to minimize, we need to use Lagrange multipliers, and the minimization problem reduces to this. Okay, so these guys, alpha i's, are Lagrange multipliers. I'm pretty sure you don't know what they are, or you don't remember what they mean actually. Just try to follow. You don't need to understand everything. Just try to understand what I'm trying to do, and at the end we will see a very basic thing basically. So in order to use Lagrange multipliers, we need to take the derivatives with respect to unknowns. We have two unknowns here. The first one is W and the second one is B, right? So xi are basically our samples. Yi is a term we introduced. We know these guys. We don't know B, we don't know W, which means we need to take the derivative with respect to these guys. So if we take the derivative with respect to W, from this we obtain this guy, okay, and from this we obtain W is equal to the sigma alpha I yi xi, which actually means W consists of linear sum of samples. This is important, guys. This part is important. W consists of linear sum of the samples, okay. And if we take the derivative of this equation with respect to B, what we have is here. So we have a second equation here that we will be using. So if we take the derivative with respect to W, we have this equation. If we take the derivative of L with respect to B, we have this equation. Now we substitute our findings into the main equation, which is this one. So this is our minimization equation basically. So if we substitute this equation and this equation into this one, we get something like this. So this looks like a pretty complicated formula, which actually it is. And you cannot solve this algebraically. You can just need to use numerical analysis, but we will not going to go into the details of the numerical analysis. Just remember this formula, and there is just one part of this formula which is important that you should remember. It is this part, this xi dot xj. Okay, so the whole minimization process, whatever we did up until now, depends on the dot product of samples. Okay, what we are trying to do is just related with the dot product of samples. And if we do this in second dimension, for example, this will be a linear support vector machine, and we will be using other dimensions for the dot product. But just the basic idea, the whole support vector machine stuff just depends on the dot product of samples. Okay, so the whole derivation, these very complicated formulas, is just to understand the relationship between the dot product and the samples. So the dot product of samples is important for the support vector machines, and the dimension we will be doing this dot product is also important. So support vector machine maps training sets examples to points in space so that to maximize the width of the gap between the two categories. That's what was the definition of the support vector machines. And we have seen the derivation of support vector machines. Now let's try to do some coding just to see how we can deal with support vector machines with scikit-learn and pandas. Okay, so we have a helper function. That's a function I provided so that you can plot decision functions for 2D support vector machines. When we say decision functions, you see this is the median line. Okay, and these are the gutters. And the support vector machine, if you want to draw something about a support vector machine, you would like to both draw the median line or the median. Let's not say this is the line, but let's say this is the median. And we would like to draw the gutters as well. These are the support vectors. So you would like to draw these three things. And this function I provided you right here, that's drawing that supports and the median. Okay, so remember our very basic example, the very basic data sets with two classes. We will be working on that in this example as well. So we assign the column names and we are assigning stuff to x and y. Something important here, if you want to use support vector machines from scikit-learn, that's basically called SVC for some reason. So it's not just SVM, scikit-learn.svm, but you need to import SVC. And we did our import. Similar to everything we have seen up until now, we first create a model and then we fit or we learn from our data set with this model. And there are two arguments here with support vector machine. Something, let's say, magical called kernel right now. We will be seeing what that kernel is actually. Just we would like to assign linear right now. And this is a regularization term. If you remember regularization from our previous lectures, if we have noise in our data, we introduce some error terms so that our regression takes place in a better way. Okay, and we will be seeing what that kernel is. But for now, we created our model here, and then we will be fitting into our model. So that was pretty quick. Now we will be plotting our support vector machine. Oops, something was wrong. Okay, we didn't obviously introduce this. Now we can plot it. Okay. You see, these are our points. Class 1, this is class 1, this is class 0. this is our median. I'm not saying this is median line, this is our median, and these are our gutters. Remember our custom line, what we have obtained, this is the same dataset. Okay, it's the same dataset, but as you see, the result is much better right now because we mathematically maximized this gap so that any point that falls within here, for example, will be classified as class 1. Any point that falls here in this area, that will be classified as class 0. So that was basically our very simple initial example about support vector machines. Okay, now let's work on another example that we will be linearly splitting. So this is a sample that we generated. Okay, this make blobs, that's another function from scikit-learn. You can basically create this kind of data with make blobs. We created 50 samples that's centered around a point with a non-random state, and then we plotted these guys. This is pretty linearly separable, right? If we have any line over here, it's gonna be linearly separated. We're doing the same thing. Basically, this time we introduced the error term pretty big. That doesn't matter really too much for examples this simple. And then we basically created, we fitted our model, and then we're plotting the support vector machine and its support vectors, its gutters, the median and its gutters. We obtain something like this. So if you look at the plots carefully, we have the gutters passing through these points. We always have at least one point because this is the maximum width that you can obtain, and in order to maximize this, you always have one of these points on the gutters. It's the same here. We have 2 points basically for class 0, and for class 1 we have 1 point. This one is pretty close. So this is basically how we deal with support vector machines. And if you would like to plot the support vectors, that's basically it. So these guys are these 3 lines. So we have seen something called the kernel, and we will now be seeing what that kernel means. So let's assume we created a dataset something like this. You see, it's impossible to separate this linearly, right? Whatever line you draw, that's not going to split this into two in a linear fashion. Let's try that. Let's try our support vector machines with a linear kernel, whether we will be able to fit something that's reasonable. As you see, it fitted something. This is the median. These are the gutters. There's a small dash here. This is the other gutter. It tried to do its best, but this is really bad. This is like as bad as it can get, because this is not a really linearly separable problem in its nature, because we are using 2D. So what if we were looking this in another dimension? What if, for example, we were using e to the minus x square? Now let's try to plot this. Okay, so if this was our data, right, instead of this one, this two-dimensional thing, if we had this three-dimensional thing, it was actually possible to split this linearly, right? We could just introduce a plane over here, and that plane could split the yellow parts and the red parts. So the idea behind support vector machines is basically trying to split this data in a higher dimension if it is not possible to split this data in 2 dimensions. So that's why I showed you all this mathematical derivation. Remember what I said, the whole stuff depends on the dot product of the samples. And if you take the dot product of the samples in 2 dimension, you get something like this. But if you use another dimension, such as this one, then it's possible to split this data into 2. Okay, so let's try to see the example first, and then we will see what I mean with this kernel and what I mean with this kernel trick. Okay, so we had kernel linear beforehand, and right now what we are going to use is an RBF, radial base function. That's called. We will see what that means basically. But let's, instead of using a linear kernel, let's use a radial base function as a kernel and see what will happen. So we said it's possible to split this data into 2 if we use a higher dimension. Then we use the higher dimension with our radial base function. Now we will see. So this is our median. Remember, I was not calling this as median line. This is our median. This is the curve, let's say, splitting our data into 2. And these dashed curves are our gutters. I still maximize the gap between the classes. Okay, but instead of doing this with a line, I use the radial base function. That's a polynomial, to say the least, actually. I use this polynomial to maximize this gap between these 2 classes, and right now I am able to split this data into 2 as positive and negative samples. So that's basically what support vector machines are doing. And coming back to our mathematical derivations, this is done by something called the kernel trick. So the kernel was another argument that we have provided to the support vector machines in scikit-learn. Remember, we initially provided linear as the kernel, and then we provided RBF as the kernel. So in addition to performing linear classification, support vector machines can efficiently perform a non-linear classification using what is called the kernel trick, implicitly mapping their inputs into a higher dimensional feature space. So what we did with our example, instead of using 2D, we used 3D, right? We used a higher dimension. And the way we were able to do that was to get the dot products of the samples in a higher dimension. So that's called the kernel trick. Okay. So remember our ultra super great formula that we tried beforehand. And the whole idea behind this very complicated formula was the whole minimization process depends on the dot product of samples. So the whole process depends on the dot products of samples. And a kernel is just a function that maps the data to a higher dimension where data is separable. Remember our example, in 2 dimensions it was not separable, in 3 dimensions it was separable. Kernel functions accept inputs in the original lower dimension space and returns the dot product. So this part is important. Return the dot product of the transform vectors in the higher dimensional space. So the kernel, what it is just doing is taking the dot product of the samples, but it can get the dot products in 2D as usual vectors, or it can do this in higher dimensions. So we have some well-known kernels actually. If we have a vector such as this one, a is equal to a1, a2, the linear kernel is the normal kernel. Okay, that's just basically the 2-dimensional dot product if you use a linear kernel. If you use a kernel polynomial 2-degree, second-degree polynomial, then our kernel is something like this. Okay, and this is basically how your decision gets affected from using a kernel, linear kernel, you obtain something like this. If you use a polynomial kernel, second degree, you obtain something like this. If you use a kernel with a higher degree polynomial, then you obtain a more complicated decision boundary. So that's basically the idea behind the kernel trick, and this is basically how support vector machines work. They just get the dot products of the samples in a higher dimension. And depending on the dimension, if the problem is separable, I'm not saying linearly separable, if the problem is separable in that dimension, then support vector machines can classify your data. And they can do this in a very good way. So we have some polynomial kernel functions that's homogeneous. This is inhomogeneous because we have an error term here for regularization. Remember what regularization was. And this is basically the radial base function. That's e to the minus x square. You can think this as e to the minus x square, as we did in our example. That's carrying out it's 2-dimension to 3-dimension, and that's creating a radial curve. Okay, that's basically what kernel trick is. So if you use a non-linear kernel, then you can split non-linear classes. If your problem is not linearly separable, then you should try a kernel that's not linear. That's basically the idea behind support vector machines. Okay, so before the multi-class classification, let's do more examples about the support vector machines. Let's do a recap. This was our problem beforehand. This was not linearly separable, at least in 2 dimensions. And once we use the radial base function, it carried these yellow dots into 3-dimension with e to the x square. And with a radial base function support vector machine, we were able to split our data as yellow and red classes, right? These are very simple examples. Now let's work on a little more complicated example. This is the Pima Indian diabetes dataset I provided you last week. So we had 2, 4, 6, 8 columns, 8 independent variables on our class. First, let's import our libraries. And then we read our CSV file and we assign the column names as we do usual. And if you look at the head of the data frame, the first 5 rows, you can see we have our independent variables on different spaces. For example, this is age, that's ranging from 0 to infinity. That's integer, that's a floating point. And these are our class identifiers. So the first row is from class 1, the second row is from class 2. So we will be using just 2 columns as our independent variables. We will be using this PGC and age, and obviously as y we need to use the class because these are our class identifiers. Let's try to plot this with the function I provided you. So this is basically pretty difficult to separate linearly, right? You can just put a line here and then it's going to split, but I mean, this is not an easy problem as a linear classifier. So what we had seen in the last week's lecture, instead of using all the data, we were splitting them into train and test set, right? And this train test split from scikit-learn was basically doing that. So let's use our train test split, and let's take a look at what we have in our training data. The first row of the training data, that's 150 and 54. You can just check 150 and 54 as our first row. And then we did something different last week. See, we used a standard scaler that was scaling our data between 0 and 1, right? Because we have independent variables from different spaces, right? So, for example, this is 148. This is quite big than this one, right? But that doesn't mean this number is more important than this one, or this independent variable is more important than this one. So this is basically a floating point that's not even one, right? If we don't scale these guys, then H or this PGC will be dominating everything, because it looks like these are more important than these guys. So in order to avoid this, for classification problems, we need to scale our data. And we can scale our data between -1 and 1, or we can scale our data, which is easier, to between 0 and 1. And what we will be doing right now is we will be scaling our data between 0 and 1. So this is basically doing that. So this was the first row of data. Let's check what happened to that. You see that's something between 0 and 1. So we just basically scale it, not between 0 and 1, but we scaled it with respect to our highest element in our columns. Okay. So now we will be creating our classifier. First, let's create a linear support vector machine. Again, we just define the model and then we fit our model. And then let's create what we had done. So it gave us something like this. That's as good as it can get with a support vector machine with linear kernel. Basically, that's a line splitting our yellow class and the red class. Now let's use our performance evaluation metrics as we did in the previous lecture. We will be calculating confusion metrics. We will be calculating precision score, recall score, and F1 score, as well as we will be seeing something called cross-validation. So from model selection of scikit-learn, this week we will be using something called cross-validation score and cross-validation predict. That's basically something we have seen last week, as in the k-fold splitting the data. Instead of using everything in our data, with cross-validation we split our data into, for example, 10. You can use different numbers here. That means instead of doing the evaluation on everything, just split your data into 10 parts and do the evaluation in these 10 parts. Okay. So let me import these guys, and since we have basically 10 parts, we split our training data into 10 parts, we will have 10 accuracy scores here. Let's see whether that's correct. Let's check. There's that shape. You see that's 10. We have 10 numbers because we have 10 different splits over the training set. And with cross-validation predict, that's basically the same stuff as the model.predict, but that's again not using everything inside the training data, but it's splitting this. This time it's splitting this into 3. And it's calculating the prediction from these 3 sets. Now let's print the confusion metrics. Remember our confusion metrics from the previous lecture. And from that confusion metrics, we can calculate the precision and recall and F1 score. And you can use this functions from scikit-learn in order to calculate precision recall and F1 score. You don't need to rewrite everything from scratch. So this is basically what you obtained. Precision score, not too bad. Recall score, not too bad. F1 score, since these are too close to each other, as you see, F1 score is close to these guys as well. But this was for the training set. Let's see what happens with the test set. So this time, I'm not gonna use cross validation since we don't have too many elements in our test set. We will just be using the model's predict function. Then we will be plotting the confusion matrix, and then we have our precision recall and F1 scores for our data for the test set. That's pretty close actually to the training set, which means the classifier worked fine enough and it was generalizable, which means what we obtained for the training sets we could use for the test set. If you get numbers close to each other for precision recall and F1 score for training and test sets, that means your model worked well enough. And this is basically what we have for the test set. So this is the median, and these are the gutters, as you see. Since these guys are the class 0, all the yellows that are on the left side of the median are classified as red dots as well, which means these guys are false positives if you want to classify the yellow dots. And the same is here. If you want to classify the red dots, all these red dots on the right side of the median, they're false positives for the red dots as well. Okay, so let's see something called multi-class classification. Up until now, what we did is binary classification. We had two classes, positives and negatives, zeros and one. We only had two classes, right? In multi-class classification, we have more than two classes. For example, if you want to use MNIST database for classification, we had 10 digits, right? We have from 0 to 9, we have 10 digits. And that means there are 10 classes for MNIST dataset. So multi-class classification deals with multiple classes, more than two classes. And there are two strategies to do that. We have binary transformation, which means we use a binary classifier, but we use it with a different strategy, or we use native multi-class classifiers. And these are two different strategies. So what I mean with binary transformation, assume that you have 4 or 5 classes, right? This is not a binary classification, such as logistic regression or support vector machines. Both logistic regression and support vector machines are used for binary classification. But assume that we would like to solve a more complicated problem. Then we can use a binary classifier on 1 versus 1 basis, or 1 versus rest, or 1 versus all basis. What does that mean? You can make a classifier, for example, that classifies whether something is purple or blue, and then purple or green, purple or yellow. That's 1 versus 1 classifier. You train a lot of classifiers. You train, for example, basically 6 classifiers to solve this problem. That's one thing, one strategy, 1 versus 1. Or you can do something as we did in the previous lecture. For example, what we did was we classified whether a digit is 0 or non-zero. Right? That's 1 versus rest, or 1 versus all. In this example, for example, you can create a classifier, a binary classifier, purple versus the rest of the colors, or blue versus the rest of the colors, green versus the rest of the colors. And by using this For binary classifiers, you can classify the color of the samples. Okay, so this is basically using binary classifiers to solve multi-class classification problems. That's another example with basically fruits. And the second strategy you can follow if you want to solve a multi-class classification problem, then you can use native multi-class classifiers. So these guys over here, naive Bayes, decision trees, k-nearest neighbors, ensemble models, and neural networks, these are by nature multi-class classifiers. So you don't need to deal with anything. You can just provide them multi-class samples, and then you can basically use them for multi-class classification. From next week, we will start with decision trees, and we will see all of these classifiers. But for today's lecture, we will continue with examples that are binary class classifiers, but we will convert these multi-class classifiers into multi-class classification problems. For now, for this multi-class example, we will be using support vector machines, again with the strategy 1-to-1. We will be using the iris datasets. If you remember it from our second lecture, that was the dataset. We started working on pandas and working with plots. So we basically import our libraries concerning NumPy, pandas, seaborn dataset, and we import support vector machine from scikit-learn, and then we read our data. And if you remember our data, the column names were not given, so we assigned the column names as well. And then let's take a look at the first 5 rows of our data. We have we are not going to use the sepal length and sepal width. Just to make things a little bit less complicated, we will just going to use petal length and petal width. That's what we did here. Okay, we dropped this first 2 columns. We have 3 columns now. The first 2 are petal length, petal width, and the last one is the species. So this species we will be using as the class. Okay, and if you remember from our second lecture, we have 3 classes in this species, and in order to see how many classes we have, we use this command. Okay, data frame species, that's the name of the column. Data frame column species unique. That's giving us all the different possible class names. And remember, it was Iris setosa, Iris versicolor, and Iris virginica. We have 3 different classes for this problem. So this is not a binary classification problem. This is a multi-class classification problem. Okay, so we will be using just petal length and petal width for the X. Therefore, we drop the species column. We will be just using these 2 columns, and we assign this to X. Now we need to do a trick. Since we are not dealing with letters, this class name doesn't mean anything to scikit-learn. Okay, and this doesn't mean anything to scikit-learn either. We need to assign numbers, and that's what we do basically. We assign 0 to Iris setosa, we assign 1 to Iris versicolor, we assign 2 to Iris virginica, and we create a temporary data frame with this mapping, and then we assign this data frame to Y. Okay, and if you basically look at our data, that's what we have, an X, and we have the species in our Y. So let's try to plot this to see what we will have. Remember, we had three classes, and we have three classes here, right? And the x and y axis are basically petal length and petal width. And as you see, it's almost linearly separable. So these two classes are pretty linearly separable, and this is kind of linearly separable apart from these guys from yellow class and these guys from orange class. If you have a line over here, that's splitting in a very good way. So this is not a very difficult problem for linear separation, but this is a good problem for multi-class example. As we did earlier, we will be splitting our data into train and test set. That's what we do with this command, if you remember. And let's check what we have in the first row of our data. We have petal length, petal width for the X train first row, right? And again, we have different spaces with for these guys, so it's a good idea to scale your data. It's always a good idea to scale your data, by the way. If you're not using linear regression or some sort of regression, then you don't need to scale your data. But if you are doing classification, it's always a good idea to scale your data. And once we scale our data, as you see, it's 5.5 became 0.9, this 1.8 became 0.73. Okay, so let's use different kernels to see how they are performing with our problem. So we will be first using a linear kernel with support vector machine, and we are using a relatively small error term, and we will be fitting our data. Then we will be using the evaluation methods we have seen in the previous lecture. With cross validation, we will be calculating the accuracy standard deviation. We will be calculating precision, recall, and F1 score. Just for the sake of coding, we press Shift Enter, and then this is our model, the support vector machine model. This is the standardized training data. This is white train. We will be splitting our data into 10, and we are calculating the accuracy with these guys, and we will be calculating the mean accuracy. Then we will be using the precision recall and F1 score commands of Python in order to calculate these terms. So we have a quite good accuracy. That's something we would expect because this is not a very difficult problem. Things were pretty linearly separable, and the standard deviation for the accuracy is pretty small. We have a standard deviation because we calculated the accuracy from 10 different splits. Now let's do the same thing for the test set as well. It's a little bit smaller. The numbers are a little bit smaller than the training set. That's expected because this is the training set. I mean, it needs to be higher. But it's again a pretty good model, and it's doing pretty well since neither the accuracy nor the precision recall scores didn't fall too much. Let's try to do the same thing with a polynomial kernel. Remember, this was a linear kernel, and now we will be using a polynomial kernel. Again, we are using a pretty small error function. That's a degree 3 polynomial. That's highly likely that it's gonna overfit. And what I mean with overfitting to this data is it's gonna try to model this, and that's gonna make errors most probably. So let's create our model. Let's train it first, and then let's make a cross validation with our training data sets. It's almost same with the training data. It didn't rise or fall basically. Let's try it with the test set. With the test set, you see the scores are a little bit less than the previous linear kernel. If you check at the F1 score, it's 0.88 for the test set. And when we check the F1 score for the linear kernel, that's 0.92. As I said, it's overfitting because that's a third degree polynomial, and this is a pretty linear problem. And since we are using a polynomial kernel, it's trying to model this little needed things, and it's overfitting. And since it's overfitting, its test performance is lower than the linear kernel. So that's basically how we actually use a polynomial kernel. You just everything is same. Basically, everything is same. You create your model, but instead of assigning a linear kernel, you assign a polynomial kernel. When you assign a polynomial kernel, you actually give its degree. By default, if you use a polynomial function, polynomial kernel, then you have a second degree polynomial by default. If you want to use a higher degree polynomial kernel, then you need to give it by hand, right? And it's basically the same with the radial base function. That's a more complicated function than a polynomial. Instead of saying polynomial or linear, we just say that's going to be a radial base function. Let's try to see the result for that as well. If you check the precision recall values with the radial base function, that's slightly better for the training set. That's slightly better than the previous models. Okay, let's see what happens with the test set. That's quite similar actually to the linear kernel. 929. Let's check what was it. It's definitely better than the polynomial kernel, and it's exactly the same as the linear kernel. So the radial base function gave quite similar results for the test data set as the linear kernel. To sum up, basically, that's how we use the support vector machines with our data. We assign a kernel. If the kernel needs additional parameters, we assign them, such as the degree of the polynomial. And we need to be careful about selecting the kernel. In order to select the right kernel, it's a good idea to choose different kernels and then get the one that performs better. Usually radial base functions are used in support vector machines, but if your problem is not that complicated, you can go for polynomial or even linear kernels. So just as a last example for today's lecture, I would like to go through the MNIST database from the last week's lecture. So if you remember the MNIST database, that was a handwritten digits database. We had 10 classes, 0, 1, 2, 3, blah, blah, and 9. And the aim of the last week's lecture was to create a classifier that can classify whether a given number is a 0 or non-zero. Okay. And for today's lecture, we will make a multi-class classifier that will say whether a digit is a 0 or a 1 or a 2. So we will have 10 classes basically. Okay, first we have these functions to load our data sets, and then by using our function we will be loading our data from our zip files. That will take a little bit of time. And then if you remember from the previous lecture, we shuffle our data because the structure of our data is we have zeros and then we have ones, we have then twos. If we don't shuffle, that affects the training phase of our classifiers. Therefore, we shuffle our data for the training. So this was the shuffling phase. Okay, and remember our data was images, 28 by 28 images. But since scikit-learn is not using two-dimensional data, we were reshaping our training and X-test and X-training, our images, into row-wise vectors. Okay, we converted our images into row vectors. Then we scale our images, and that's basically we import support vector machine from scikit-learn. I'm not gonna fit the data, that takes quite some time. You can try this. I will be providing all the data and the Jupyter notebook, so I'm not gonna press shift enter here, but I will be showing you something else. If you create a model that takes time, and more complicated models takes more time. For example, when we start dealing with neural networks, that's gonna take minutes, sometimes hours, sometimes days. So you don't want to lose your model. By using this fit function, we create our model. So we need to store our model for future use, okay? And once we store our model, we can basically load our model. We use pickle dump, and we use this dump to write our model, okay? And then we use pickle load in order to load our model. So I already wrote my model into hard drive. I hope I will be able to load my model, and then I will be basically using my loaded model in order to calculate the precision recall F1 scores, and we will be seeing whether it was classifying things correctly. So if you look at the F1 score, recall and precision score, my model is pretty good. Actually, that's 90% F score. That means it's doing its job in a good way. So we have our predictions basically inside this ytestpred function variable. Let's see how it basically performs. So inside the 7th index, we have a 9. Okay, so let's see what's our prediction. Our prediction is a 9 as well. Let's see in our 10, 9th, that's a 9 as well. Let's see our prediction. Our prediction is a 9 as well. Let's say that's 8. That's 8. You see, there's a problem here. Our prediction confused this digit 5 to handwritten digit 5 with a handwritten digit 6. So that's why we have we don't have a 100% precision and 100% recall. We obviously did some mistakes. We couldn't classify some guys correctly, and that's one of them. Originally, the thing was a 5, a handwritten digit 5, but we could be able to classify this as a 6. Let's see, for example, 18, that's a 3, and we classified this as a 2, for example. This is a mistake as well. So our model is not perfect, but our model is kind of doing fine. So I strongly suggest you train your own model. Just execute this line, and then try to use pickle to save your model and load your model. To be familiar with loading and saving models, we will be using this a lot once we start with neural networks, because the more complicated model you use, it takes more time to basically train, and you don't want to put your model into wastebasket once you switch off your computer. So just to try to understand this pickle dump and pickle load stuff, you need to be able to write your model, and you need to be able to load a previously written model. So let's make a brief summary of this week's lecture, and then we will have our quiz. Then we will call this the day. So we have seen a concept called linear separability. We have seen that these clusters can be linearly separated, as well as this one, but neither this one nor this one can be separated linearly, because there is no single line that can separate this class from this blue class. Okay. And then we have seen the concept of support vector machines. We said that support vector machines are trying to maximize the gap between two classes. And we have seen the mathematical derivation of support vector machines. Then we made a simple example that was perfectly separating these two classes. And now what we have seen is we can use basically the support vector machines in order to classify more complicated linearly non-separable problems by using something called the kernel trick. And what kernel trick was basically doing is making use of the mathematical definition of support vector machines. Support vector machines were basically using the dot products of samples. And if we take the dot products of samples in a higher dimension, then it's possible to solve linearly non-separable problems, such as this one. So we use a radial base function here. Instead of taking the dot products in two dimensions, such as this one, we use e to the minus x as the radial base function. And once we get the dot products in that dimension, it was possible to split this cluster from this cluster. And we did quite a few examples about support vector machines and how we can use them with scikit-learn. And then we worked on the concept of multi-class classification. We said we can use a binary classifier for multi-class classification, as well as we can use naive classifiers. And for using a binary classifier for multi-class problem, we have two strategies. Either we can train one-to-one, one versus one classifiers, or we can train one versus rest classifiers. And we lastly did two examples with support vector machines with one versus all examples. We made a 3-class example, and after that we made a 10-class MNIST database example. So that was it for today's lecture.